Hi everyone. Today we're going to be talking about polynomial integration. This is the first and most basic type of integration technique that you'll usually learn in a calculus class. The first thing that I want to talk about is just a couple of notes on integration. When you see that indefinite integral sign, which looks like this, graphically, you would think find the area under the curve. But when we don't have a graph, instead of thinking area under the curve, we're thinking find the antiderivative. So what we're really doing is differentiating backwards. We're kind of going from a first derivative maybe to an original function, depending on the application that eventually you'll end up looking at. Polynomial integration, the focus of today's video, is essentially the power rule for integrals. We can only use this integration technique when all of the terms that we're integrating are separated by addition and subtraction signs. If our terms have other operations going on between them, we'll need different integration techniques that I'll talk about in some subsequent videos. Let's look at our rule for polynomial integration. When we do polynomial integration, we're essentially doing the power rule that we used for differentiation backwards. So rather than taking that exponent, multiplying by 1 and subtracting, like we would when we're finding a derivative, instead we add 1 to the exponent and divide by that new exponent. So when we differentiate, we multiply and subtract. When we integrate, we add and divide. So it's opposite operations. Here are two important algebraic rules that will come in handy when we're using polynomial integration. One says if you have a radical, you can rewrite that radical as a fractional exponent. And our next algebraic rule that's helpful is if you have some kind of variable in the denominator of a fraction, you can bring that variable to the numerator by negating that exponent. Some basic integration properties that we might find helpful today: factoring out a constant, and if we have terms that are being added and subtracted, we can separate them over multiple integrals if necessary. Let's look at our first example. Here is our first example for polynomial integration. Since all of my terms, these three terms, are separated by addition and subtraction signs, I know that I can apply this polynomial integration technique. I start by carrying down the constant of 10, or the coefficient of 10. I add 1 to this exponent, x to the fifth, and I divide by that new exponent, 5. I'll do the same thing to the 2x cubed. I add 1 to the exponent, and I divide by that new exponent. Last, carry down the 4x, I add 1 to the exponent, so now it's squared, and I divide by that new exponent, 2. When we integrate, we have to remember to add in a plus c. This plus c represents some constant that I could have taken the derivative of and wound up with 0, which is why there's nothing accounted for here. So we account for a possible constant by putting in this plus c. Every time you integrate, once you drop that integral sign, you add in a plus c. Every line that you rewrite should have an integral and a dx, or a plus c, one or the other. I'm going to clean this up a little bit to get a final answer. 10 divided by 5, I have 2x to the fifth. 2 over 4 is a half, so this would be x to the fourth over 2. And 4 divided by 2 would be 2x squared. Don't forget that plus c. So this would be our final answer for this first example. Let's look at one that's a little bit more tricky. Number 2, I want to integrate 3x plus 5 squared. I'm going to start by expanding out the 3x plus 5 so that all of my terms will be separated by addition and subtraction. Right now, since this binomial is being squared, I can't integrate just yet. When I multiply this out, I would get 9x squared plus 30x plus 25. So I've just rewritten the expression that I'm trying to integrate. I haven't yet integrated. In my next step, now that my terms are separated by addition signs, I can integrate each term using polynomial integration. So for this first term, I'm going to bring down the 9. I add 1 to the exponent, x cubed, and divide by that new exponent, 3. I do the same thing for the 30x, so it would be 30x to the second divided by 2. And for the 25, we can think of this as having maybe an x to the 0 next to it. So if I add 1 to that exponent, I would have 25x to the first and divided by 1, which I'm not going to write because that would just be a waste of space. And then I'm going to add on this plus c. I'll clean this up a little bit. So I have 3x cubed plus 15x squared plus 25x plus c. That will be my final answer for number 2. Let's look at another example. Number 3, when I integrate this expression, I'm going to need some of those algebra rules that we talked about in the beginning of the video. I'm going to rewrite this integral the same way that I would rewrite something that I wanted to take the derivative of. I can't integrate with this variable in the denominator, and I can't integrate with this radical in the way. So if I rewrite my integral sign, I have 2x to the negative fourth minus x to the half plus 3. Once I've rewritten and all of my terms are separated by addition and subtraction signs, I can start integrating. I'm going to add 1 to the exponent of negative 4. Negative 4 plus 1 is negative 3, and I divide by negative 3. When I deal with my fractional exponent, I'm going to have that subtraction sign carry down, and I'm going to leave space for a fraction here. When I add 1 to the exponent, a half plus 1 is 3 halves. Using this rule here, I would divide by 3 over 2. But we don't want a complex fraction that looks super sloppy. So instead of dividing by 3 halves, we can multiply by the reciprocal 2/3. For the plus 3, I integrate, I get plus 3x. Don't forget to tack on that plus c. I'm going to rewrite with positive exponents. We don't like to leave negative exponents in our answers. So I'll have negative 2 over 3x cubed minus 2/3 x to the 3 halves plus 3x plus c. There's my final answer for number 3. Let's look at another example. Number 4. I have some division going on here, so I can't immediately apply our polynomial integration technique. What I'm going to have to do here, since I only have this one term in the denominator, it's going to be easiest for me to divide this one term in the denominator into each term in the numerator and split these 3 terms up. When I do that, I have the integral x cubed divided by x squared. I get a 5x out front. X squared divided by x squared, those will cancel, so I just have that minus 4. And then I have 2 over x squared, so that's going to be 2x to the negative 2. Now that my terms are all separated by addition and subtraction, I don't have this denominator anymore, I can apply that polynomial integration technique. So I would have 5x squared over 2. I added 1 to the exponent of 1 and divided by that new exponent. For the 4, I tack on an x. And for the 2x to the negative 2, I would have 2x to the negative 1, negative 2 plus 1, and divide by that new exponent of negative 1. Don't forget to add on that plus c. I'm going to rewrite this term with a positive exponent. So my final answer will be 5x squared over 2 minus 4x minus 2 over x plus c. Number 5. This is about as complicated as a polynomial integration will get. We have a radical in a denominator, we have another variable in a denominator, and 2 other radicals floating around. I'm going to start by rewriting this whole integral with fractional exponents and or negative exponents. When I rewrite my first term, I have 3x to the negative 1/3. My second term becomes 4x to the half. My third term is 3x to the negative fifth, and my last term would be x to the 4/3. So all I've done so far is rewrite the terms that I'm trying to integrate. I have not integrated or applied polynomial integration. In my next line, since I'm separated all by addition and subtraction signs, now I'll start adding 1 to the exponent and dividing by that new exponent. So now I start my polynomial integration. For this first term, I'm going to carry down the 3, leave space for that fraction, and write my x variable. When I add 1 to negative 1/3, negative 1/3 plus 1 would be plus 3 over 3, so that new exponent is positive 2/3. And again, rather than dividing by 2/3, because that would look pretty sloppy, I'm going to multiply by the reciprocal 3 halves instead. For my second term, I carry down the 4, leave space for my fraction, carry down that variable. If I add 1 to a half, 1 over 2 plus 2 over 2, I get 3 over 2 for my fractional exponent, and I multiply by the reciprocal of 2/3. plus this next term, if I add 1 to -5, I have x to the -4th divided by -4. And my last term, again, I'll leave space for a fraction. 4/3 plus 3/3 is 7/3. And I multiply by the reciprocal, 3/7. Don't forget to tack on your plus c. I'm going to clean this up, multiply out some of these fractions, and make sure that I write all positive exponents in my final line. So my final answer here, I'm going to have 9/2, x to the 2/3, plus 4 times 2, so I have 8/3, x to the 3/2. So I'm going to make this a subtraction sign in between, and I would have 3/4 x to the +4, making this negative exponent positive. And this last term I can just carry down as is, minus 3/7, x to the 7/3 plus c. That is my final answer for number 5. That's it for polynomial integration. I will leave a link to some other videos using other integration techniques if you need. If you have any questions, feel free to ask them in the comments below. Have a great day.